Hi there, thanks for joining us for this second video in chapter 2. This is where we're going to actually start talking about sort of the fundamental things we need to understand to be able to understand organic reactions. Really, for this applies to really any sort of chemical reactions, but especially useful things to understand organic reactions. And I think any amount of effort you can put into mastering this foundational stuff will be really will help you for the rest of the year, the whole year of okay. These are things that you will repeatedly encounter in this class. So, first of all, I think last week or in the last video we talked about how the mechanistic pathway or the mechanism of the reaction is really important because the kinetics tends to explain why you get certain products. Like you might get this less stable of a product if the mechanism is such that you don't have to go through as high of an activation energy and so forth, right? And so for that reason, in organic chemistry, we tend to focus a lot. In fact, most of the year will be spent discussing mechanisms of organic reactions and figuring out why these reactions happen the way they do, because that's going to really help us understand organic chemistry really well. So that's going to be the focus, to be able to come up with a mechanism to explain why a particular reaction happens and how that reaction happens. And of course, as we said, all the chemical reactions, right, involve valence electrons. The core electrons, they're just gonna stay there, and the protons in the nucleus, they're not gonna move. When those things actually move or change, that's called nuclear reactions, like nuclear bomb. We're not talking about those kinds of reactions here in this class, and so for that reason, basically the only thing that changes in chemical reaction are the electrons, valence electrons. So to explain a chemical reaction, we just have to explain what happens to the valence electrons, and that's it. And so because of that, it's nice to show the movement of electrons with a particular notation, and we call those curved arrows because they're arrows that are curved in organic chemistry. So what do curved arrows mean, right? Like they explain the movement of two electrons typically, okay, and they have this type of appearance. And I want you to notice how it's a double-headed arrow. This means two electrons are moving, and I want to emphasize that it's the movement of electrons, not atoms, because atoms technically don't move around independently per se, and it's the electrons that move around to break a bond and to form a bond, right? Because all the chemical bonds that are being broken and formed, those are only come from electrons. Okay. Oops. And in our class, I'll try to stick to this convention for me that I tend to draw the electron arrows with the blue color. And how do those things behave, the electrons? Well, I want you to think about it. Electrons are negatively charged things, right? So it should make sense to you that they flow from negative charge places or partial negative charge atoms or bonds to positively charged atoms or electrophilic or partially positive things, right? And the atom that the arrow originates from I hope this makes sense, that because electrons are moving from there to form a bond with something else, it's going to lose an electron essentially, right? The charge becomes +1. the atom at the destination of the arrow, or the movement of those electrons, usually gain a -1 charge because they gained an electron. And usually that's to form a bond. And I hope this also makes sense that arrows must start either at a lone pair or a bond that's breakable. So arrows only start at a lone pair. It's the electrons that are available, or a bond. Usually it's a pi bond. Okay, that's easier to break. So this almost explains like a third of organic chemistry right here, if you could just remember this and master it, really understand it. We are going to use this curved arrow convention to explain many different reactions, but they, for the most part, fall into these 4 categories here: dissociation, coordination, substitution, and addition reactions. So what is a dissociation reaction? It would look like this, with a generic reaction of a molecule made of A and B atoms, and then this literally dissociates into perhaps a cation and an anion. Right, if that were to happen, I want you to notice that this bond broke, right, that are made of 2 electrons. And can you guess which way those electrons moved to make this reaction happen? They must have moved to the atom B, right? Because atom B gained negative charge because it gained electrons. A lost electrons. So hopefully that makes sense to you. And this is an example of what we would call heterolysis. Lysis means breakup. It's a bond being broken up, and it's hetero or different because one atom lost electrons, one atom gained electrons. So unequal distribution of electrons, so hence heterolysis. Okay, examples of that, and there's an example that would be considered homolysis or homolysis, where two atoms get 1 electron each to break up a bond, but we won't think about that until the end of the semester. An example of heterolysis type of dissociation would be something like this, where electronegative atom gets the electrons like halide and becomes an anion, meeting the octet like that, and the carbon here gets a positive charge instead. Okay, so I want you to notice this is an entropy driven reaction example, because we went from 1 to 2 particles. Right, that's usually the driving force for dissociation type of a reaction. Coordination reaction is just another fancy way of saying formation of a new bond. Okay, so how does that happen? An example would be like cation A might react with anion B. But in this case, what we're saying is, maybe I should draw the lone pair to be explicit. If B has this lone pair, you might use that lone pair of electrons to form a bond. So I want you to notice how this bond came from the lone pair of electrons. Okay, and this would be an example of coordination. In this case, we might say this is Lewis acid. A is an example of Lewis acid, and it's an electrophilic. And B is an example of a Lewis base, and it's nucleophilic. Nucleophile just means nucleus loving. And what's in the nucleus? It's the positive charges. So I hope it makes sense that negative charge, right, seeks out positive charges. So what's an example of this? Well, the carbon cation that we talked about earlier is indeed able to react with an anion like this. So that what that tells you is this reaction is actually reversible. Right. And what would this reaction be driven by? Well, it's entropically unfavored, but enthalpically it's favored because we are gaining a new bond. Right. So hopefully that makes sense. And another example might be of a reaction might be called substitution reaction. And for this, let's think about a generic halide, like that's represented by this symbol X. So this is a nucleophile. How do I know it's a nucleophile? Because it's got a negative charge. That means it's got excess electrons. And to be fair, it doesn't have to be a halide to be nucleophilic. But let's say there's a molecule where you have these partial charges because B is more electronegative. In that case, nucleophile might be attracted to attack this electrophilic atom A, and that would kick off the B atom because A could not have so many bonds at the same time. Then you would have formed this new X to A bond, and B would be separated or dissociated. So that's an example of a substitution reaction. An example might look like this. Hydroxide ion attacking methyl group that's bonded to chlorine, which is of course electro negative, very much so. That makes this carbon C is very electrophilic, and so substitution reaction is possible where chloride gets kicked off and you can form this methanol alcohol and the chloride anion leaves. Okay, so that's an example of a substitution reaction, and you could see what got substituted, right? Chlorine was substituted by this HO or hydroxide group. Okay, and the last type of reaction would be addition reaction. Okay, and that's when you have a couple different flavors. So there's the nucleophilic, addition, and then there's the electrophilic addition, and we'll look at both. And let's say we have this generic nucleophile, we'll just say NU, and then there's this A to B double bond where A is electrophilic and B is an electronegative element. Then what can happen is this could add here like so. And this is aided by the fact that B wants more electrons anyway because it's electronegative. Then you would have this situation. And B gains an extra lone pair. And okay. So that would be called a nucleophilic addition. and in the process pi bond broke. But I want you to notice we gained a sigma bond. So this, is it entropy or enthalpy driven? If you guessed enthalpy, you would be right, because you gained a sigma bond at the cost of a pi bond. So that's a good thing, right? The sigma bonds are stronger. So what's some example of that? Hydroxide anion, as you'll learn, is a pretty nucleophilic thing. This compound's called formaldehyde, but I hope you could appreciate how there would be a partial positive charge on the carbon, partial negative on oxygen. You would also know this because you could draw a resonance structure where there's a full positive charge in carbon and full negative charge on oxygen, which tells us that there's this negative characteristic on oxygen, positive characteristic on carbon. So then carbon is electrophilic, that can be attacked or added to by a nucleophilic hydroxide, and the pi bond breaks. And the end result will be this structure here, and this of course would be enthalpy driven reaction. And the last flavor of addition reaction is the electrophilic addition. And what that would look like is if you have this very electrophilic cation Y, let's say that this is an electrophile. That means it wants electrons, and remember pi bonds are weak, right? So electrophile could grab those electrons in the pi bond because they're not very tightly bound to the atoms. They're weak. It's a weak bond. And what happens is that's how Y gets added to A and B, right? In the process, A might lose the electrons. B, I want you to notice, is losing these electrons, but it's gaining a bond, so charge doesn't, there's no change in the charge, whereas A lost this pi bond, and instead it didn't even get to gain a bond, so it's going to gain a positive charge. It lost electrons. So this is an example of an electrophilic addition. An example might be if you have a proton, right, which is electrophilic, that might grab pi electrons in a double bond or alkene, and that would result in this carbocation situation. And again, this is also enthalpy driven because you're gaining a bond. Okay, this is definitely not favored by entropy. Alright, so I'll see you in the next video.